One of the most common problems with concrete is cracking. This tape deals with recommendations for how you can avoid cracks in slabs on grade. I'm Harvey Haynes, a consulting concrete engineer. This tape is the second tape of a two-part series on avoiding cracks in slabs on grade. The purpose of this tape is to provide recommendations on how to avoid or minimize cracks. The tape stands alone and can be viewed without seeing tape number 1, which covered the topic of why various types of cracks occur. However, I think it's important to understand the why of crack formation, especially from thermal and shrinkage behavior of concrete. So I strongly encourage you to watch tape number 1. Spot decisions can be made in the field when you understand the reasons why something happens. This tape does not cover the reasons, just the what to do. Here is an overview of avoiding cracks in slabs on grade. Tape number 1 covers the various types of cracks and their fundamental causes. Tape number 2, this tape, covers recommendations to avoid these types of cracks. Under recommendations, I'll discuss how to avoid cracks from soil movement, thermal behavior of concrete, and shrinkage behavior of concrete. Let's start with soil movement. I'll cover soil heave and settlement. Heave is from expansive clays. Under heave, we'll consider the following items: clay moisture content, floating slabs, and reinforcing steel. Clayey soils need to start out in a moist condition that is above the optimum moisture content. Now in the field, you're not going to be able to tell what the optimum moisture content is. So you just have to make sure that the clay is damp. In preparation for placing concrete, it can take a couple of days of constant flooding or irrigation to get the clay in this damp state. Don't place concrete on top of dry, expansive clayey soils. When the clay gains moisture, it swells and easily lifts concrete slabs. For this reason, the slabs should be floating or independent of building foundations. I'm talking about such slabs as walkways, patios, and garage slabs. Place isolation joint material between the slab and the building. The joint material is usually 1/2 inch thick fiberboard. Make sure the fiberboard goes all the way through the thickness of the slab. This way the slab is floating on the soil, and for any heave, the slab freely rides on top of the soil. Yes, the slab will move, and that will be undesirable. But if the slab were tied into the building with tie bars or dowels, consequences would be considerably worse. For walkways or patios that are tied into the building, they can be reverse slopes as the free end is picked up. I recommend using reinforcing steel bars in slabs to control crack size, to distribute the cracks, and to prevent vertical offsets. Now, vertical offsets are where the slab on one side of a crack is higher than a slab on the other side of the crack, and that presents a tripping hazard. A recommended amount of steel for 4-inch thick slabs would be number 3 bars at 18-inch spacing. That's in each direction. And for 5-inch slabs, number 4 bars at 24-inch spacing. That's enough on heave. I'd like to say a few things about settlement. Under soil settlement, we can avoid cracks in slabs by providing a firm and uniform support or by increasing the thickness of the slab. Base rock is used to provide a firm support for the slab, and it's especially good for supporting the edges. Now, base rock is typically a 4-inch thickness of compacted gravel. If it's not used, and sometimes it's not, then the native soil must be strong enough to support the slab appropriately, even when the soil is wet. A thicker slab will also resist cracks from settlement. A 5-inch thick slab is 50% stronger than a 4-inch thick slab. I'd stay away from a 4-inch slab if the strength of the native soil is in question or the loads on the slab are not well defined. That extra inch does not cost that much for the added insurance. That covers soil movement. Let's move on to thermal behavior. These topics follow those covered in tape number 1. Under thermal behavior of concrete, there are 3 main causes of cracking. I'll cover recommendations to prevent cracking due to seasonal temperature change, daily temperature change, and heat of hydration. Under seasonal temperature change, concrete slabs move due to major swings in temperature between summer and winter. Joints are provided to accommodate this movement. The different types of joints are contraction or control joints. Now these terms are interchangeable. Control joints are really the common term, but the American Concrete Institute is encouraging a shift to the term contraction joint. So that's the term that I'm using. Then there are expansion or isolation joints. These joints look exactly alike. And finally, construction joints. Let's go over each type. A contraction joint is an intentionally weakened section in the slab so that the crack occurs at that location. The recommendation is that the weakened section be 1/4 the thickness of the slab. Concrete that is cast in the summer and then exposed to cold winter temperatures will contract or shorten. As that contraction occurs, it's the weakened section that will crack and therefore prevent unsightly random cracks in the slab. Expansion joints use a compressible material, such as fiberboard, that go through the entire thickness of the slab. Concrete that is cast in the winter and then exposed to hotter summer temperatures, it increases in length, it expands. That is where the compressible material comes into play. It allows the concrete to expand. The recommendation is to space expansion joints from 50 to 100 feet apart. I have seen sidewalks having expansion joints at a 20-foot spacing, and that is unnecessarily close. Construction joints are locations where new concrete interfaces with existing concrete. Now these joints can be designed as contraction joints when bond breaker is used on the existing concrete face and smooth dowels or keyways are used. The joints are not designed as contraction joints when the existing concrete is called to have a roughened face and continuous rebar or tie bars join together the existing concrete to the new concrete. That covers the types of joints that allow movement due to seasonal temperature change. The next 2 items for discussion under thermal conditions can be treated together. They are the daily temperature change and heat of hydration. Daily temperature change is the thermal cycle between hot sun and cool evening. Combine this with a heat of hydration that is generated in the fresh, young concrete, and cracks can occur within 1 day of age. Now the way that happens is, first day, the concrete hardens and becomes hot. The cool evening temperatures come, concrete contracts. That contraction can cause cracks in this weak concrete. What is required is to make sure that the contraction joints are installed on the first day before the cool evening temperatures. So that's a very important recommendation. Contraction joints must be installed on the first day. That covers thermal cracking. Let's move to the next major cause of cracking, shrinkage. Under shrinkage, I'll cover preventing crazing cracks, preventing plastic shrinkage cracks and minimizing drying shrinkage cracks. Let's start out with crazing cracks. Crazing consists of very fine surface cracks. Here's an example. The recommendations to prevent crazing cracks are rather straightforward. It's all in the finishing operations. Light tamping, no overworking, and don't sprinkle dry cement on the surface. First, if the concrete is tamped, it needs to be tamped lightly, because if it isn't, the aggregate particles are pushed down too far and a thick paste layer on the surface will result. It's the paste layer that crazes. And second, don't overwork the concrete during finishing operations, because this will bring additional fines to the top surface, especially if water has been sprinkled on the top to aid in the finishing operation. And third, never sprinkle dry cement in the hopes of absorbing bleed water and therefore trying to speed up the finishing operation. If you want to remove bleed water, either drag it off or vacuum it up. And especially don't finish the surface while some bleed water still remains. Now let's move to plastic shrinkage cracks. Plastic shrinkage cracks occur from too much moisture being lost from concrete that is fresh or in a plastic consistency. Here's an example. To prevent plastic shrinkage cracks, focus needs to be on two factors: on hot and windy weather conditions and the finishing operations. Let me say a couple of things about weather conditions. Windy weather or hot weather should be a signal that extra care needs to be taken in working with concrete. If too much water evaporates from fresh or plastic concrete, then the plastic shrinkage cracks can develop. I'll make a couple of recommendations about low concrete temperatures, rapid placement, and avoiding the hot part of the day. First, the concrete temperature itself should be kept as low as possible. Transit mixed trucks in a standby mode should be directed to wait in the shade, if available. The drum itself can be sprayed with water carried on the truck so that evaporative cooling can hold down the temperature gain. Second is rapid placement, which means having a sufficient crew size so that concrete can be placed, finished, and curing compound applied as rapidly as possible. The third point is to avoid the hot part of the day by considering a change in the work schedule. That means placing concrete in the early evening instead of the early morning. Starting work at 6 a.m. is good for the workmen, but not for the concrete, because the young concrete then is exposed to the hottest part of the day. By starting work at 6 p.m., that is good for the concrete, because the concrete then experiences cooler ambient temperatures. Let's move on now to finishing operations. Under finishing operations, the desired task is to delay the evaporation of bleed water. As long as bleed water exists on the surface of concrete, you know this water is evaporating. Once bleed water is gone, then water is being withdrawn from within the pores of concrete, and this is not good. This causes shrinkage, and after maybe an hour or two, plastic shrinkage cracks can develop. There are two recommendations for delaying evaporation. One is fog spray, and the other is applying an evaporation control coating. Mist nozzles are used for creating fog spray. They cause the relative humidity of the air to be increased, thereby reducing the evaporation rate. This is a good method. The second and easier method is to apply an evaporation control coating. This is not a curing compound. The material gets sprayed on the concrete after bull floating. And later, when the concrete is ready for further finishing operations, the coating does not interfere. The practical aspect of this approach is that a 5-gallon can be stored on your truck and used only on those days when needed. And what are those days? The hot and the windy days. We now move to minimizing drying shrinkage cracks. The topics we'll consider in this section are the concrete mix design, vapor barriers, contraction joints, reinforcement, and curing. Let's take them one by one. For mix design, I'll discuss 2 items that have a significant effect on shrinkage. The first item is to minimize the water content in concrete, and the second is to use as large an aggregate particle size as possible. The amount of water in concrete is the number 1 factor in defining the shrinkage characteristics of a certain mix. The objective is to use the minimum amount of water. As a contractor, you have control on how much water is placed in concrete in the field. For slabs on grade, a 5-inch slump should be maximum, unless mid-range or high-range water-reducing admixtures were used in the mix. The more water that's added to concrete, the higher the shrinkage values, and therefore the higher the probability of more cracks. The next recommendation is to use concrete with as large an aggregate size as possible. If the slab is 5 inches and concrete is available with a maximum size aggregate of 1.5 inches, then use it. The reason is that with larger aggregate sizes, less cement paste is used in the mix. That means lower shrinkage values for the concrete and fewer cracks. Now, turn this around. If you use concrete with a maximum size of aggregate of 3/8 of an inch, this is called pea gravel concrete. You can expect high to very high values of shrinkage. Pea gravel concrete has a high cement content and usually a high water content. And for these reasons, the slab is likely to show a lot of cracking. A reason why pea gravel concrete is used is so that a small, low-cost pump can be used. Now, I have found that even though the cost of the pump is low, the cost of the concrete is high because of the extra cement used in the mix. I encourage contractors to use a larger capacity pump, one that can handle concrete with 3/4 of an inch maximum size aggregate. Here, the pump costs more, but the concrete costs less than pea gravel concrete. So cost-wise, they either break even, they may even come out a little ahead, and they have a concrete that has lower shrinkage values. The next topic is vapor barrier. I'll discuss open drain rock, sand over plastic sheeting, and plastic sheeting by itself. Vapor barriers are needed under slabs in living areas, such as in residential homes, so that moisture in the ground cannot rise and come in contact with the bottom of the concrete slab. If moisture does contact the bottom of the slab, it'll rise through the concrete and mold can grow underneath linoleum and even carpet. So vapor barriers are meant to prevent this problem. One approach is to use open drain rock, which is clean, 3/4 of an inch rock having a depth of at least 4 inches. This provides a good capillary break between the ground and the concrete. I like this system. Another vapor barrier system is plastic sheeting, also called visqueen, that is covered with 2 inches of clean, damp sand. The visqueen is placed directly on the ground or on top of open drain rock. The sand serves several purposes. It protects the visqueen while the workmen move about. It allows excess water to drain out of the bottom of freshly cast concrete, and it assists in curing the concrete by supplying moisture from below. If care is not exercised, this approach can cause cracks in the slab. The sand is displaced easily, and concrete discharged from a pump hose can push sand and cause sand ridges. These ridges look like contraction joints to the slab. and a crack will follow from ridge to ridge. So from the top surface, it looks like a random crack. This problem can be avoided by making sure that the sand is damp before placing concrete and that concrete discharged from a pump lands on top of existing concrete that has already been placed. Using plastic sheeting all by itself, that is without the sand, has been discouraged by the industry. Years ago, a study was done that showed slabs had more cracks when the concrete was cast directly on the plastic sheeting as opposed to being cast on plastic sheeting with sand. As a consequence, plastic sheeting has been shunned as a vapor barrier. I don't think we need to be afraid of plastic sheeting as long as we know what we're doing. I used it at my house. 2 layers of 6mm visqueen without any sand. The key is the concrete needs to have a low slump. There can't be excessive water in the concrete. If you use a high slump material and there is excessive water, there will be extra cracks because this extra water can't drain out the bottom of the fresh concrete. So watch the quality of the concrete, meaning keep the water content low. The next recommendation is the use of contraction joints. Contraction joints are a topic of major significance in avoiding cracks on grade. Pay attention to this section. I'll cover the topics of the different types of contraction joints, their spacing, and layout. Let's start with the different types of contraction joints. These are saw cuts, inserts, tooled, scored, or grooved joints. We'll start with saw cuts. Saw cuts are good because they can be cut in straight lines and to the proper depth. The disadvantage of saw cuts are that they are usually installed the day after the concrete is cast. Cracking can occur that first night due to thermal contraction. So if you use saw cuts, make sure they are installed the same day that the concrete is cast. This is especially important if the weather is warm or hot. There is a product on the market that can cut fresh concrete. As soon as the final finishing operation of the concrete is complete, this saw can cut the contraction joint. Let's talk about inserts. Inserts are plastic strips that are inserted into the fresh concrete. They work well because the contraction joint is installed into fresh concrete. The disadvantages are that the material is rather flimsy, so it's difficult to install them in straight lines. Also, there are times where it's difficult to push the insert into the concrete because aggregate particles don't move away. So the insert gets kicked to its side, and the concrete can start breaking away from wheel loads or traffic right here in this top narrow area. Tooled, scored, or grooved joints are the names found on drawings for joints to be installed into fresh concrete. The method works well because the joints are installed right away in the fresh material. The disadvantage is that the joints are more than likely not of the required depth. Contraction joint spacing is a most important topic. A close spacing of joints will minimize random cracks better than any other method. This table has been around for a long time, and if it were followed, there would be far fewer problems. Now in California, there are a lot of tilt-up buildings, and the slabs to those buildings follow the interior slab criteria, meaning for a 5-inch slab, the joint spacing is never placed any closer than 20 feet. And that's not correct. It should be following the exterior criteria, where the joint spacing is never any greater than 13 feet. The reason for this is that the slabs are constructed in an exterior environment, and only later do the slabs become interior. Where in other parts of the country, due to snow, rain, the walls and the roofs are constructed first, and then the slab is placed. That is a true interior slab. Some patios and walkways are called out as 4-inch thick slabs. But in actuality, they're only 3.5 inch. So the 10-foot joint spacing actually needs to be closer. If 6 feet were used, there would be far fewer random cracks. If pea gravel concrete is used, then the joint spacing shown in the table needs to be closer. Each value in the table should be reduced by at least 3 feet. Take a look at this diagram on contraction joint layout. Joint layout is best if there are square sections, but this isn't always practical. If you need to use rectangular sections, make sure that the length is not more than 1.5 times the width. Re-entry corners crack easily, so make sure that they get jointed properly. This arrangement is a conventional layout where the joints are just an extension of the slab. I show this other layout as being an acceptable alternative. A summary statement is in order for contraction joints. Don't ignore or minimize this topic. Errors can be made in other areas, such as adding too much water to the concrete, and cracks will still be minimized because of a close spacing of joints. The small extra cost of adding additional joints is your best insurance policy that the slabs will not be removed and replaced because owners aren't happy with random cracking. As a reminder, we're in the major subject area of minimizing drying shrinkage cracks, and we've covered the topics of mixed design, vapor barriers, and control joints. The next subject we're moving into is reinforcement, and then finally curing. Under reinforcement, there are several types: welded wire mesh, rebar, steel fibers, and polypropylene or nylon fibers. To start the discussion, it's important to understand a few things. There is no code requirement for steel reinforcement in slabs-on-grade. That means you don't have to use any reinforcement. Now, if you do, the reason for steel reinforcement is to control crack size. The reinforcement will not prevent cracks. It'll only control the size of the crack. Let's start with mesh. Welded wire mesh or fabric does little in controlling drying shrinkage cracks. The typical mesh used in slabs provides such a low percentage of steel reinforcement that it really doesn't do much. The one thing that it does is provide some assistance in preventing vertical offsets at cracks. Another aspect of welded wire mesh is that it is generally located in the bottom of the slab. Workmen placing concrete are stepping on it and keep it to the bottom. Now, any steel reinforcement that's located on the bottom of a slab provides little in controlling crack size. I generally do not recommend using welded wire mesh. Let's cover rebar. Steel reinforcing bars are good because they can be placed up high in the slab, and the proper location is up high. Here's the reason why. Because of curling, the crack width is highest or widest at the top and narrowest at the bottom. When the reinforcing bars are placed low in a slab, they're not doing anything in controlling the crack width where we see it at the top of the slab. So when reinforcement is placed high, it is providing value in controlling the crack width and keeping it narrow at the top where we see it. A guide for properly placing reinforcing bars in the slab is to provide 2 inches of clear cover on top of the reinforcement. Now, dobies are usually used for chairing up the rebar. And a problem with dobies is that they're placed on top of the sand. And as workmen walk around on the rebar, the dobies are vibrated and they settle down into the sand. The result is that the steel reinforcement is too low in the slab. What needs to happen is the dobies need to be sized for no sand, and during installation the sand gets pushed aside. In thick slabs, to get the steel high enough, it may be necessary to double up on the dobies. The amount of steel provided by rebar is almost always more than that provided by wire mesh. The engineer typically turns to the code and pulls out the minimum amount required for temperature and shrinkage reinforcement in structural concrete. Now remember, I've mentioned for slabs on grade, we don't require any reinforcement. But this amount of reinforcement does a fair job on controlling crack size. However, if you're interested in controlling crack width to the fullest extent possible, then the design is going to need to provide 3 times the amount of this minimum temperature and shrinkage reinforcement given by the code. Let's move on to steel fiber reinforcement. I really like steel fiber reinforcement. These little fibers are added to the concrete mix, transit mix truck and mixed in with the other concrete ingredients. The concrete is placed and finished using normal procedures. The fibers control cracks as the cracks start forming at real local levels. It's very efficient. About 30 to 50 pounds of fibers are used per cubic yard as a minimum. The cost is a little more than that of rebar or wire mesh, but it's money well spent because of the effectiveness of crack control. Polypropylene and nylon fibers have a beneficial effect to concrete in minimizing plastic shrinkage cracks, not for drying shrinkage cracks. These fibers are added to the transit mix truck, and the mixing action distributes the fibers. They're added at a rate of about 1 pound per cubic yard. Technically, the fibers are so rubber band-like compared to concrete that they do not reinforce concrete the way steel does. The fibers are marketed as a replacement for welded wire mesh, and I'm okay with that approach because the mesh provides so little. At least these fibers provide something in minimizing or delaying the plastic shrinkage cracking. That completes our section on reinforcement. We'll move to the last section on curing. The objective of curing is to allow for strength gain of concrete and to delay drying shrinkage cracks. This is done by making sure that water is in the pores of concrete. The definition of curing is to provide an environment for concrete that allows for continued strength gain, which can only be done if the cement hydration process is continued and water is required for that. Also, with the presence of water, drying shrinkage isn't going to occur. Now eventually, the concrete will lose moisture, dry out, and shrink. But by that time, the concrete will be stronger and it just won't crack as easily. The best curing method is that of wet curing, where water is applied by sprinklers or flooding. The more conventional method of spraying on curing compound to hold a mixed water within the pores of concrete, that's only a fair method, but it is practical and it's low cost. Another advantage of the curing compound is that it can be applied immediately after the final finishing operation, whereas wet curing would require a delay. Now, if the weather is windy or hot, the coverage rate should be increased to about 1.5 times that recommended by the manufacturer. Also, if the surface is rough due to a broom finish as opposed to a hard troweled smooth finish, then the coverage rate should also be increased. That covers curing, and it also completes the topic of shrinkage. To review, we covered how to prevent crazing cracks, how to prevent plastic shrinkage cracks, and how to minimize drying shrinkage cracks. Now let's review the big picture. In this tape, I have provided recommendations on how to avoid cracks from 3 common causes: soil movement, thermal behavior of concrete, and shrinkage behavior of concrete. This completes tape number 2 on recommendations on how to avoid cracks in slabs on grade. Tape number 1 covered the fundamental causes of concrete cracks. I'm Harvey Haynes, and I hope that these 2 tapes have provided a good understanding on how to avoid concrete cracks in slabs on grade.